Okay, so what is the heart of complex analysis, right? So functional analysis or complex function theory in two variables begins with the heart of complex analysis, which is the Cauchy integral formula. So Cauchy integral formula you would have seen in an undergraduate complex analysis class, and again in graduate school, but it contains a lot of the, where the hell? It contains a lot of the basic themes of everything that comes after. So to remind you, the Cauchy integral formula says that if you have an open domain in the complex plane and you have a disk that's inside this, right? So a disk contained in here, the basic idea is that for everything inside that disk, every complex value inside the disk, the value of the function, so the value of f, is determined by the boundary. So you integrate around the boundary of the disk, and that tells you the value of every function on the inside. So the big theme here is that there's this interplay between boundary behavior of a function and the complex analytic behavior on the interior of the domain. And that's kind of what I want to talk about today, is techniques that involve looking at boundary behavior and thinking about the analytic behavior on the interior of a domain, or studying boundary behavior by looking at the complex analytic behavior on the interior and pushing it out to the boundary. Okay, so we're going to be looking at the relationship between values of f on a boundary and values of f on the interior. In classical complex analysis, particularly the work of the early 1920s and early 1930s where this stuff was born, you have these classical domains that are studied. The notation that I'm going to use here is D for the disk, H is going to stand for the complex right half plane, and pi is the complex upper half plane. So you can think here that we've got the disk, the right half plane, and the upper half plane. And one of the powerful things about this type of work is that if you prove a result in one domain in complex analysis, then typically you can carry some or all of that result into other domains by way of what's called the Cayley transform, which is a conformal map that moves you between these domains. And one of the central things that was noticed about early complex analysis was if you proved something about functions on the upper half plane, you could move that result into functions, into a result about functions on the disk. So classes of functions that were studied by the early functional analysts are, these are the names that we use in this community. Sometimes these names vary from community to community, so you have to be careful because Nevin Linna, Pick, Herglotz, and Schur get tossed around depending on if you're talking about control theorists or analysts or people that are working in partial differential equations. So for us, a Schur function is going to be an analytic function that is a self-map of the disk. A Herglotz function will take the disk into the right half plane, and a Pick function is going to take the upper half plane into itself. And just like the Cayley transform gets you from domain to domain, you can also use the Cayley transform on the output of the functions as well, so on the input or the output. So you can apply these to the input or the output of various functions. And that actually lets you, that's what lets you move functional information from class to class. And so there are ways that you can slide back and forth between these classes using the Cayley transform as well. And that dance lets you take advantage of some of the structural features that these functions have. So where does modern functional analysis in the vein of Agler begin? So the Herglotz representation formula is a way of writing down a Herglotz function, that is characterizing functions that take the disk into the right half plane in terms of an integral against a measure. So a Herglotz function is a function that takes the disk, remember this thing right here, this is a Herglotz function. So if you take the disk into the right half plane, that you can do that if and only if. So this is a complete characterization of the Herglotz functions. F can be represented as this integral, where you've got what's called this is the Poisson kernel against this measure mu, and that integral representation holds not just, or that holds for every z on the disk. So you should recognize that this is thematically similar to the Cauchy integral transform because this integral is a boundary integral. Right? This measure is a measure on the boundary. You're crawling around the boundary and it's telling you something about the behavior of the function on the interior. So similar results hold for things, or let me talk a little bit about the structure of why these things are so interesting. So where is the information about f in an integral representation? Well, the kernel, you can think of, that's identical, right? The kernel is the same no matter what f you're dealing with if you're in the Herglotz class. And so the kernel somehow is telling you where the class inclusion comes from. So the structure of the kernel of the integral, or the integrand, puts you in the Herglotz class. So any other information about f must live in the measure. So the function theory of f can be studied by looking at the behavior of mu. And this is the sort of big idea of classical one-variable functional analysis. The kernel gets you into the functional class. The measure is what you study to understand individual functions or more refined behavior. Okay, so another example of an integral representation that underlies an enormous amount of work is called the Cauchy transform. So Nev and Linney used the Cauchy transform to study the hamburger moment problem, which suggests a connection to probability, which it has. And so the idea here is we can get slightly more refined behavior, or we can study functions in a class with slightly more refined behavior, and then we get integral representations that correspond to that. So what we're starting with here, if f is analytic and f takes the upper half plane into the complex plane, so that's, we hypothesize that, then f is a pick function. So this right here says that f is pick. Plus, f satisfies a boundary condition at infinity. So this is an integral at infinity, but remember, when you're thinking about the complex upper half plane, infinity is one of the boundary values, right? If you conformally transform that back to the disk, it explicitly corresponds to one of the points on the circle. So the Cauchy transform set is a way of characterizing pick functions that satisfy a growth condition at the boundary. And if you have that, then you get this very straightforward integral representation, where again, you have this kernel and a representing measure. So the Cauchy transform in particular is an enormously powerful thing to look at, even in one variable. And why? Well, on the one hand, you get this incredibly rich analytic theory of pick functions that you can use, right? So it's got an immediate application to complex analysis. At the same time, it's a boundary integral. So while this function this transform is only defined on the upper half plane, you can push it down to the boundary to study the behavior of pick functions that have this form on the real line in the complex plane. On the other hand, the Cauchy transform is one of the fundamental objects of probability theory. So you get this sort of three-way relationship where you've got complex analysis, boundary behavior, and probability that are all linked together through this integral representation. Okay, so what sort of boundary behavior can you study with representations that look like this? So there's a whole sequence of results about boundary behavior that sort of motivate a lot of the work in several complex variables. So the first result is due to Fatou. And essentially the question is, if I know f is analytic, so if I know that I can reconstruct, if I'm on the boundary and I've got an understanding of the boundary values, I can reconstruct what happens in the interior using integral representations or the Cauchy integral transform. Well, what about the other direction? What if you have a function that's analytic, right? So now we've got an analytic function. What can we say about the boundary? What can we say? So the first result along these lines is due to Fatou. And a very straightforward version of the Fatou theorem says that if you have a bounded function on the disk that's holomorphic, then you can find non-tangential limits for almost every point on the circle. So non-tangential, you should just think of as being, there's a wedge, which is called a Stolz region, with its tip at the boundary point that you're interested in. And to approach the boundary non-tangentially just means that you're approaching the boundary in some sort of wedge like that. Okay? So Fatou's theorem is if you approach non-tangentially for a bounded analytic function on the disk, you have boundary limits almost everywhere. A more sophisticated theorem looks at boundary regularity or boundary differentiability. So Julia and Carathéodory and Wolff in the late 1920s and early 1930s built a theorem that talks about okay, so we know that these bounded functions on the disk have limits. Can we find some sort of conformal derivative, right? Some sort of linear approximation near a boundary point. After all, if a function is analytic in the interior, it says nothing about its behavior on the boundary, right? So what Julia and Carathéodory together showed is that if you have a Schur function, so that is f takes the disk into the disk, then this inequality being bounded, so this is called the Julia quotient. So if the Julia quotient for the function is bounded as you approach the boundary, a boundary point non-tangentially, that happens if and only if a limit exists and also a derivative exists. And this derivative is called an angular derivative. And that locally, that is on a Stolz region intersected with a small disk around your boundary point, that you actually have a linear approximation for your function. So that's sort of a step above the Fatou theorem. Now, this is the first point where I'm going to say that there's an enormous literature, current literature on Julia Carathéodory theorems, even in one variable. So if you're interested here, the author to look at is Bolotnikov, and he has a list of collaborators that he works with. And after the talk is over, there may be people in the room that can suggest more places you might look if you're interested in looking at boundary regularity. Another one variable theorem that followed from the work on integral representations is a theorem called Loevner's theorem. So Loevner's theorem is a theorem about matrix monotonicity. So if you have A and B that are self-adjoint matrices, so symmetric matrices, then you can put an order on those by saying A is less than or equal to B if B minus A is positive semi-definite, which means that A is less than or equal to B if when you subtract them from each other, you only get positive or non-negative eigenvalues. So in a theorem of 1934 and a later proof due to Neven-Linna, you suppose that you have a function that is real valued on some interval a to b, and as you can evaluate a function on an interval a to b on matrices as long as the eigenvalues of the matrix fall in that interval. So what Loevner's theorem says is a real valued function actually extends to be an analytic function, or is a boundary, it's the boundary of an analytic function, if and only if, I guess I should say as a function in the PIC class, if and only if f preserves these matrix inequalities, which is to say f is a PIC function, or f extends to be a PIC function on the upper half plane if and only if f is matrix monotone. Loevner's approach to this was technical and matrix analytic and basically very difficult to generalize to other contexts. Neven-Linna's insight was that you could redo this problem using integral transforms. Okay, and that's a much more broadly applicable technique. So now the question is, great, if you've got integral transforms, you can build all these theorems about boundary regularity in a lot of surprising directions. Well, what happens when you move to two variables? So the issue is, I would like to study the two variable Schur functions and the two variable Herglotz functions and the two variable PIC functions, and I'm hoping that I can recover, so the hope is that you can recover results of classical analysis. The issue is that integral representations in two variables are incredibly difficult to understand. So if you're interested in seeing what that looks like, so if you want to see why is this hard, why are measures hard? You can look at a sequence of papers due to Vladimirov, and more recently Lugar and Nedich, where they do integral representations in terms of measure theory. The problem is that the way that the measures interact with each other when you're thinking about two variables is very difficult to tease out what that does at the boundary, okay? And so there's a limit where when we look at proofs that involve measure theory of integral representations in one variable, they don't obviously generalize to two variables in an easy way. So we're going to need some other tool. Okay. So what can we do? So sort of the entry point to this at the larger level is a paper of Agler of 1990 called Representations of Herglotz Functions. And this is where Agler's model theory really sort of gets wielded, right? Put together in a way that's sort of unified. This is a paper you might, this is a very clear paper if you haven't read it before. And Agler had already used operator theory to work on the Neven-Linapic interpolation problem, but this sort of codifies the representation theory or the realization theory of Hilbert space models. So what did he do? Well, he noticed that the Herglotz representation, so this is the Herglotz representation, that he could take the Herglotz representation and using the spectral theorem, so using the idea that self-adjoint operators can be represented as measures in one variable, he took the Herglotz representation and he just rewrote it as an operator expression. So this is just the Herglotz or the Poisson kernel, an operator Poisson kernel. And he embedded all this in a Hilbert space that essentially, because of the spectral theorem, is an exact analog of the classical Herglotz theorem. Okay. Now, you might think to yourself, oh, where do these U's come from? Well, these are unitary operators. Well, the unitary operators just corresponds to these e to the I thetas up here, right? E to the I thetas on the circle, circles correspond to unitary operators. There you go, right? The measure itself, you can think of, where did the measure go? Well, the measure is the V star and the V on the outside, right? Because essentially what's going on there is you've got a Hilbert space and an inner product. In the case where V is just a vector, this is an inner product. Okay. So did I get something? Yeah, I missed. I forgot to put my inverse on there. So yes, you are correct. Absolutely. Thanks, Ed. Okay. So why is this any more useful? After all, it's just, so a lot of work of Saracen involves taking these sort of operator representations and redoing classical analysis with it. So what Agler noticed was, well, maybe we can take this and we can beef it up. Well, where does the idea come from? Well, there's a related idea, and here you're looking at, did I lose my, these are out of order. Okay, so what's the idea? The idea is, if I have an operator representation, there's a very obvious way of thinking about generalizing it to more than one variable. Because the z right here isn't really a z on the right-hand side, right? It's z times I. It's an operator expression where z is multiplied by some kind of identity. So you can think about it as z's being down the diagonal. So what Agler thought was, okay, and this is following from the model theory of Nage and Foyage, ultimately, which is a one-variable theory. So what Agler noticed was, I can just take this formula, and yeah, on this side, these things are complex numbers. Can I think of something that go in here that will replace the z, since z was really an operator in that expression? So it turns out that the right idea was just to say, oh, well, what if I just put z1, z2 in there? What if I take my Hilbert space, H, that this is built on, and I just break it into two pieces? And I let z1 live on one Hilbert space, and I let z2 live on the other one. That's a pretty straightforward idea, and the miracle is it works. So you take z1 and z2 and you just pop them in there as sort of a block operator. And what you end up with is what the operator we call easy. So easy here is just z1 projection onto the first Hilbert space plus z2 projection onto the second Hilbert space. It's an obvious generalization of the one variable case, because as long as the projections add up to the identity, all you're doing is taking the identity and breaking it into two projections. This continues to work in n variables, okay? With the restriction that there's an entire, you have to play games with when the functional calculus makes sense. And in more than two variables, you actually have to restrict the class that you're looking at in order for it to make sense to, for all the inequalities that drive all this to make sense, which is why two variables is best. Now, it turns out to be the case that all of the representations that you write down for functions in these various classes, the same idea applies. So if you've got a Herglotz function, you can replace z with a sum of z's times projections. If you're in the Schur class, This is called a realization. Here, the theory of transfer function realizations, there's about 1 million papers you can read here. Helton is a good place to start with this. There's papers due to Ball et al. So there's a long theory of where these come from. This is one of the big connection points to control theory and electrical engineering. Okay. And the Cauchy transform, well, remember the Cauchy transform originally looked like the integral of 1 over t minus z d mu of t. Well, this thing right here is like a Cauchy kernel, where yz now is just the operator where I take yz1 and 1 minus y, sorry, z2. Okay. Now, there's a reason why there's a contraction instead of a projection here. Has to do with the fact that in the Cauchy transform, you have this boundary behavior that you have to deal with. So the representing operators aren't projections, they are contractions instead. Okay, so where does the function behavior live? In the one variable case, we know that the functional behavior lived in mu. In the two variable case, it had to go somewhere, right? How am I going to study functions using these things? Well, the kernel, again, is sort of what gets you into the function class that you're looking at. So where do you get functional behavior in a more refined way? Well, it has to live in the Hilbert space that you build that's modeling all of this, and this particular contraction y, and this particular isometry v that represent the function. So the data that represent f in this context are Hilbert space objects instead of measures. And Hilbert space geometry in many cases is significantly easier to understand. Okay, so there's two fundamental objects that come out of Agler's 1990 paper. The first is a realization theorem for Schur functions. This is the Schur function objects. There are also representations for Herglotz functions in there. And then with some gimmicking, you can take the realization theorem and you can build something called a model equation. Oops, that's not the right pen, sorry. Right? And this lets you get back and forth between a realization of a function where you can understand f by understanding these operator pieces, and then an explicit inner product construction that sort of corresponds to a Gramian matrix. Okay? So this thing, in the same way as the model construction gets you, or the realization gets you, here's some operator objects I can use to understand f. The model formula says, well, if I want to understand f, which is, these are all numerical values over here, so these are numerical, I can do it entirely in terms of inner products. And I want to add here that the w and the z on the right-hand side, in the same way that the z that appears in operator expressions is really like an operator, these aren't somehow two variable complex numbers, right? Those are actually operators. You can think about them as being the operators that we talked about before. So they're the block operators corresponding to z1 and z2 decomposed over the Hilbert space. Okay, so now armed to the teeth with a Hilbert space way of understanding function theory in two variables, now you actually can reproduce the theorems of one complex variable. So the big idea is that if you have a proof of a one variable theorem that uses integral realizations or integral representations, and you can transform that into an operator version of the integral representations, oftentimes the proof in the two variable case is as simple as just slapping the two variable version of the integral representation in there. So what sort of results can you get? Well, remember, the Julia-Carathéodory theorem said that boundedness of the Julia quotient corresponded to sort of linear approximability locally near tau on non-tangential sets. Using in an intense application of these objects right here, so using this object and this object, realization theory and the model theory, to change the problem into a problem of essentially the geometry of a Hilbert space, Agler and Young showed a corresponding theorem for the Julia-Carathéodory theorem. This is another great paper, by the way. So there's an Agler, McCarthy, and Young paper, I think it's 2010, on the two-variable Julia-Carathéodory theorem. And what it says is, If you have a two-variable Schur function, then boundedness of the Julia quotient, so this is the two-variable Julia quotient, corresponds to f has a non-tangential limit. Well, that's the same as the one-variable theorem. But now you don't get a conformal derivative. You get a directional derivatives for every direction pointing into the disk. So what I mean here is that if you're at a point tau and you point into the disk in any direction in the half plane determined by the tangent line at the edge of the, or the tangent plane at the edge of the torus, at any direction on the inside, there's a formula you can write down for the directional derivatives. Okay. So we don't get the derivative. So where does the derivative behavior go, right? Where is f prime? Where's this angular derivative? Well, in the same way that measure theory tells you something about functions and integral representations, the model itself tells you where that went in the two-variable case. So two variables is way more complicated than one variable, which is why we need these sort of beefier tools. And so what Agler, McCarthy, and Young noticed was that you need more to get this derivative or differential regularity at the boundary. So a B point is essentially when the Julia quotient is bounded. So in terms of the model, what that means is this vector valued function up here, this vector valued function right here. So these are, try to get my highlighter. This vector valued function here, that function being bounded as you approach the boundary point corresponds to f having directional derivatives pointing into the inside. So that's the basic condition of the classical Julia-Carathéodory theorem. If you want more, if you want to recover the full Julia-Carathéodory theorem, then you need that function itself to be bounded, right? So this Hilbert space valued analytic function has to extend by continuity to the boundary point. The model is only defined on the interior of the bidisk. So there's some model condition that tells you when the function actually has this derivative structure at the boundary. So the model and regularity are related to each other. So why is the two-variable case so bad? So here is your entry point to the wonderful world of rational inner functions. So rational inner functions are functions that are even in two variables. They're rational functions that take the boundary of the bidisk, so the two torus, into the circle. That's what inner means. There's a very, very rich theory of rational inner functions. I've got some author names on the next slide. This rational inner functions are another sort of core idea of the study of analytic functions in two variables. So here's just a real basic one. It's about the simplest rational inner function you can write down. It's degree 1, 1. It obviously has a singularity at the point 1, 1, right? And it turns out to be the case it's an inner function, but it also has a Kara point. So what I mean by a Kara point is a B point. I should have clarified here. A Kara point just means a B point. Usually we try to distinguish model conditions from function conditions. And so to have a Kara point means a bounded Julia quotient. Okay, so it meets all the hypotheses of the Agler, McCarthy, and Young Julia-Carathéodory theorem. So why is it so bad? Well, in two variables, what can happen is you can have at the edge of the disk, or of the bidisk, you could have the zero set of a polynomial or of a rational function come in and hit the boundary, and you can have the polar set come in and hit the boundary, and they don't cancel each other algebraically like they do in one variable. So you get these singularities that don't cancel, and they're topologically complex. And again, so there's a sales pitch for just even in the rational case, there's a series of survey papers by Bickel and Pascoe and Sola. So that's, if they're in the room, that's Kelly and James and Alan, that goes into exhaustive detail about how these things can actually behave and what that means, the relationship between geometry and differentiability. Okay, so now in my work, I was interested in trying to improve the tool set that you could use here to study this thing. And the reason that you want to improve the tool set is that you've got this model equation. So this is the Agler model equation. Where does the singular behavior of this function have to live in this model equation? It's got to be somewhere. I mean, after all, this holds for all values of z on the interior of the bidisk, right? It is the function in some sense. So where did it go? Well, it can't be in z, because remember, z is just this real straightforward block operator. So that's not singular. That's about as nice as things come. So the problem is that it must live in the analytic functions here. So these must be badly behaved at the boundary. So what I'm proposing to do with this model is to study the boundary with something that sucks at the boundary, right? And in fact, a lot of the difficulty in the original Julia Karathi-Dori paper of Agler, McCarthy, and Young is they have to work around the fact that these functions uz don't actually extend to the boundary continuously. And so there's an enormous amount of geometry that goes into deducing what they can about the behavior of uz and uw. So the question is, well, can I do better? Okay, so now we're moving into sort of contemporary work. So this is work that I did in as part of my dissertation. It appeared in 2017 and 2012. So the papers to look at here are Agler, Tully-Doyle, and Young, 2012, and my work in 2017. So the idea is that if I have a realization, remember, every model comes with a realization, that the problem is going to be at this middle chunk, right? Because if that thing has a kernel, then that means that operator gets nasty at the boundary, potentially. So what the idea is that now we can just use, this is like sort of cutting down a measure or by like throwing away the part that you don't like, right? That you don't need. We're going to do the same thing here. We're going to cut the Hilbert space down and throw away the part that we don't need. So you get to use linear algebra, basically. So you decompose your Hilbert space so that you can just slice out the kernel of that operator, and then you drop it down at the boundary, right? So you look at what the operator would be at the boundary, you identify its kernel, and you just slice that piece out of the model. Everything is left, you just project on the good part. So that's linear algebra. But what do you get? Well, you get a way of recharacterizing boundary behavior in terms of rational inner functions. So remember, the function that we started with was not rational inner, but the function that models the boundary behavior is a rational inner function. So here we go. This thing is an operator valued rational inner function. So it's operator valued. Well, don't let that scare you. Where y is a positive contraction, it turns out to be the case that this thing has a boundary value of 1, and it meets the conditions of the care point, right? The Julia quotient of this function is bounded. So it's got that same singularity at 1, 1, but its Julia quotient is bounded as you take it out to the point 1, 1. So it has a B point. And that means that essentially every B point is in some sense contained inside this IY thing. So you can come up with this, what's called a generalized model, where the game is, now these things are continuous at the boundary, non-tangentially. And so now you're explicitly modeling singular behavior with a function that has singular behavior. So the model sort of measure analog part is continuous at the boundary, and you can understand the singularities by studying this function IY. I want to point out here that IY, if the contraction y is just the number 1/2, it's the same as the original rational function that we started with. Okay. So what do you get? That seems like a lot of work for a tool without an application. Well, you take your model, got my pen. You take your model, you can turn that into a realization, and with the realization, you can study functions that have singularities at the boundary. The beautiful thing is you get this complete characterization of the directional derivatives. And you get it entirely in terms of this sort of integral representation. So I want you to think of this as secretly an integral representation. It has the same structure as integral representation. It's got a fixed vector. We're taking an inner product against this fixed vector. It's got this kernel in terms of a positive contraction y. So the form of all of the directional derivatives is given by this special class of pick functions that we understand because we have an integral representation for it, and we can study that. So there's another sequence of papers here that use this sort of set of ideas, not just to study Schur functions, but take these ideas and conformally transform them to pick functions. So there's a bridge here between Schur functions and pick functions. So this was studied by Agler and McCarthy in a paper about what are called Hankel vector moment sequences. And I think James has a paper that I don't know if he's published, but at least in his dissertation, he had work along the same direction. Okay, so now the idea here is, let me sum up here before I go into some questions I've got. So the idea is that, so what's the big overarching theme of all this? We started with integral representations and theorems that were proved with them in one variable. We transform that into operator representations that correspond to those, and then we just try to plug sort of generalizations by thinking of Z as being a block operator into the realizations, and we end up with this rich function theory where we can actually use classical analysis as a guide. So we're not on, you know, like it's not terra incognita, right? We have a guide in classical theory because we can follow our noses with integral representations. So what do I want to know? What are some things you might think about or things you might read about if you're interested in getting started in this kind of math? So this is specifically aimed at graduate students or researchers or early researchers. So the question one is, if I have a care point at tau, then I can completely characterize the boundary regularity in terms of this sort of integral representation. So my question is, does the y contain more refined behavior? Is there, if we understand the y better, can we say more about the way that the function is defined at the boundary? And the question there comes from, you know, so the partial answer is yes, right? My follow-up paper to the building the generalized model showed that y, the operator y can actually detect whether or not, it explicitly shows how the operator y detects if the function is merely bounded or has directional derivatives, or is bona fide conformally differentiable at the boundary. So that is contained in y. Now, the exciting thing is that there's a ton of new regularity theory about the way that Schur functions can behave at the boundary. So there's work of McCarthy and Pascoe, which is called Julia-Carathy-Dory theorem revisited. There's work of Pascoe. And then in the rational inner function work of Bickel, Pascoe, and Sola, they introduce all kinds of intermediate layers of regularity, right? So new sort of steps between directional differentiability and non-tangential differentiability. So my first question is, I'd like to understand that in terms of this operator y that's sort of like the analog of the representing measure. So can I build a model theory that incorporates all of this new understanding of boundary regularity? All right, question two is about Cauchy transforms. So the Cauchy transform, which was this is sort of one of the heart of the entire enterprise of analysis objects. It connects to everything. It connects to mathematical physics. It connects to perturbation theory. It connects to an enormous amount of probability. So in two variables, you can write down something that looks like a Cauchy transform. So here it is right here, right? So this is sort of a two-variable Cauchy transform. So my question is, well, it looks like one. So is it? Does it link up with one-variable applications? There's no end to the applications of the one-variable Cauchy transform. In probability theory, actually the best book to look at this is, there's a book that was written by Seema Matheson and Ross called The Cauchy Transform that just exhaustively describes the applications of the Cauchy transform. So there's a lot of places to start looking there at things that you might think about. Okay. In the non-commutative setting, if that's more your flavor, well, you can write down a non-commutative Cauchy transform that has the same kind of structure. So don't get scared by the tensors here. It's essentially the same as the commutative Cauchy theorem. There's an inverse I missed right here. Okay, so again, it looks like a Cauchy transform, and it gives you the relationship with the function theory that corresponds to the Julia-Carathy-Dory theorem in the classical setting. So here's a big question. Why doesn't the analytic theory of free analysis match the analytic theory of free probability? So, you know, there's a paper due to Williams that builds a non-commutative Cauchy transform And James and I showed that it doesn't quite match up the same way. That the parameterization that you get in the classical case between Cauchy transforms of these measures and pick functions with the boundary behavior, this restricted boundary behavior at infinity, it doesn't match. So why not? There's a place to start digging there if you're interested in getting your feet wet in non-commutative theory. All right, finally, my final thing that I'm interested in right now is related to a problem called the Donjoy-Wolf problem, which is about applying complex functions to themselves, so repeated composition of complex functions. So in one variable, this theorem is what the Donjoy-Wolf theorem says is that if you compose a Schur function with itself over and over and over and over again, that sequence uniformly converges to a single point, assuming that you didn't start with an automorphism. Okay, that completely breaks down in two variables. It's like not even close to the same. And so one idea would be, well, there's a proof in a book of Carlson that actually used the Herglotz representation to prove the one variable. Instead of a real elementary Schwartz lemma argument, it actually uses the Herglotz representation. Well, that's one of those things that suggests maybe there's an entry point for operator theory. But in order to use it, we have to understand how we can compose realizations with themselves. And that is not something I know how to do, but I'm interested. So that has applications in complex dynamics. And so you can see that even just in this really straightforward thematic line from classical analysis, that there's a lot of questions that intersect with other areas and also classic analysis itself. So to sum, if you are interested in references, I guess you can email me, or I will provide a list about the various topics that I discussed today to Meredith to post on the OTTER webpage. I'm happy to talk to anybody who's got ideas in these areas. These are ongoing projects that I have with Kelly and James and Meredith and various other people. These ideas work a lot of times in one or several variables. So I hope that I've given some anchor points for graduate students and researchers looking for other problems to think about, and sort of why I like this kind of math. And please give feedback on the technical level of this talk and if it needs to be higher or lower so that the future talks in this sequence can be tuned appropriately. And thank you for your time.